The next topic we'll be investigating is about alternative ways to define centrality for points on a two-dimensional graph. For example, we might look at data samples from a real-life situation, or we might look at data collected from a simulation, like the one shown here. But, in either case, when we compare two groups, our results often depend on how we define constructs like centrality and spread. So, our next topic is centrality. In other activities in this section, we looked at points on a line, and we saw that a variety of different notions of centrality are useful under different circumstances. We also saw that, if we are comparing groups using notions of centrality, then results, such as which group scores higher on some measure, often depends on which notion of centrality is used. For example, for the data shown here, if we can compare the A group and the B group, and if we focus on only scores on the horizontal axis, then we can ask Tinker plots to show us both the means and the medians for these two groups. What the graph shows is that, in this case, Group B's average scores are higher, if median scores are used. But, Group A's average scores are higher, if mean scores are used. These same issues apply to points in a two-dimensional graph. And, just as for points on a line, there may be a variety of useful ways to think about the concept of centrality, which depend on your purposes. To see why, let's consider the simplest case where there are only 3 points, which can be thought of as vertices of a triangle. First, let's look at the center of gravity for the triangle. It can be found in 2 ways. One uses a geometry construction, and the other one calculates the means for the coordinates of the vertices. The geometry construction involves drawing lines from each vertex to the midpoint of the opposite side. Then, the point where these lines intersect is the center of gravity for the 3 vertices or for the triangle as a whole. Also, just as it was for points on a line, the center of gravity also minimizes the sum of the squares of the distances to a collection of data points. Second, look at the incenter for the triangle. It can be found by constructing the angle bisectors for the 3 angles of the triangle. The point where these angle bisectors intersect is the center of a circle that is inscribed within the triangle. Third, look at the center of the circle which goes through the 3 vertices of the triangle. It is called the circumcenter of the triangle. It is found by constructing the perpendicular bisectors for each of the 3 sides of the triangle. Now, there are algebraic formulas which can be used to calculate all of the centers that we've been considering. But, we've been focusing on the geometric constructions so that, later in this course, when you consider different kinds of centrality, you'll have some way of visualizing what the formulas mean. Fourth, we could consider the point where the altitudes of the triangle meet. Or, we could consider the point that minimizes the sum of the distances to each of the 3 vertices. It is the point which makes angles that are exactly 120 degrees, when lines are drawn from the point to each of the vertices. Remember, when we were looking at points on a number line, the least distance point was the median for the collection. But, in a two-dimensional space, things get a little more complicated. What is the median point for points in two-dimensional graph? We could try to find the median in one dimension and then find the median in the other dimension. But, this raises some problems. For example, this diagram shows the location of the median point. But, this is only true if the axes are horizontal and vertical. If the axes were skewed in another direction, then the location of the median point would change. This might be an asset if we were dealing with points whose axes corresponded to different kinds of factors that we want to keep separated. But, in other situations, a changing notion of centrality might be a problem. Now, we have considered 5 different notions of centrality. All are useful under some circumstances. And, all can lead to different results and conclusions if our goal is to do something like compare collections of data. For example, if notions of centrality change, then corresponding notions of spread from this center also change. So, when you are measuring either centrality or spread, it's important to know what you are measuring and what assumptions you are making. In particular, throughout this course, it often will be true that centrality and spread can be based on sums of squares. Or, they also can be based on sums of simple straight line distances. And, different ways of measuring generally lead to different results. Every statistic is based on a model. And, every model is based on assumptions that may or may not want to make. So, as we begin to use more and more fancy statistical functions, it will be increasingly important to be aware of assumptions that underlie our work.